We're going to start by doing a little bit of reviewing. Mirrors are solid surfaces that reflect light. So in this diagram that I have here, I have a couple of arrows and a couple of symbols, and we need to make sure that everybody is clear on what these letters and symbols are. Mr. Filsinger, tell me about that green arrow. What would I call that? It's not a wave front because it's a light ray. Remember, rays are signified by arrows. That was in the vodcast that you were to have watched if you missed class yesterday. The arrows are the light rays. So how would I describe, or what would I name this green arrow? Nathan, can you help him out? An incident light ray. Yeah, there's this little eye here, isn't it? So this is the incident light ray. What's this funny looking circle with a line through it represent? Trevor. Theta. What does theta represent? Angle. So this angle here is called what? Matt. Incident angle. Exactly. It's the angle between my incident light ray and this line right here. What's this line called right here? Just says it's perpendicular, so what would I call that line where the blue arrow is pointed? Normal, Mitch says. Lines that are perpendicular to surfaces are normal lines. We've learned that way back when we learned about forces, right? So there's the normal. The incident angle, again, is the angle between the incident light ray and the normal. So Hunter, what's this orange line over here all about? It is the reflected light ray, exactly. So this is the reflected light ray. And the angle between it and the normal is the angle of reflection. Ben Filsinger, what's the relationship between the incident angle and the reflected angle? They're equal? Yes, they are. Incident angle is equal to reflected angle. Is this new stuff? No, we talked about this when we talked about waves in general. So our incident angle is equal to our reflected angle. That's not new stuff. So let's take a look at types of reflection. We have two ways that light can be reflected. We have something called specular reflection. Specular reflection is from surfaces that are smooth and usually shiny. The red lines are my incident light rays, and the blue light rays are going to be my reflected light rays. Incident light rays are coming in parallel to each other. They hit the surface and they get reflected. So my reflected light rays also can be parallel to each other. Reflected light rays that are parallel to each other give me very sharp, clear images. So here is the scene, here is the reflection. Almost as good as a mirror, not quite. Matt, what can you tell about the weather at this location based on this image that we see? It's calm. How do you know it's calm? Yeah, there's very hardly minimal ripples in here. So I've got a nice clear edges to my image, smooth surface, specular reflection. So anything smooth and many times shiny will give you that. Mirrors, glass. If you're looking at a window pane and you can see your reflection, is a specular, creating a specular reflection. Car surfaces, water, if it's smooth, all can create specular reflection. The other kind of reflection I can have is diffuse reflection. I get diffuse reflection when I have a rough surface, and some surfaces are more rough than others. When the light reflects off of rough surfaces, the angle of reflection is equal to the angle of incidence in each case. So there's one light ray reflecting there. This one's going to reflect like that. That's going to reflect like that. That's going to reflect like that. So my reflected light rays are scattered. Depending on how rough the surface is, depending on how much scattering I get, I'm going to see an image or not. So here I have water again. Because I have ripples in my surface, it's going to be probably breezier here. And so I get some image and I can see pretty much what the object is, but the lines are blurry. It's much harder to see it. If I have a really rough surface, say the lawn, the road, how much reflection do you get off of that? None. So then I get complete scattering of my light. No image is reflected, and that's a completely diffuse reflection of light. So those are two terms that you need to be familiar with when we're talking about reflection, the type of reflection I get, either specular reflection or diffuse reflection. When we're dealing with mirrors, we're going to be dealing primarily with specular reflection. All right? Let's take a look at a mirror and how do we see images in that mirror. What did we say yesterday we used for an object? Julian, do you remember? An arrow, exactly. So let's use an arrow. So that's going to be our object. What we want to do is draw an image of that in our mirror. The mirror that we're going to be working with, folks, is called a plane mirror. Plane mirrors are simply flat mirrors. And when you think plane mirror, I want you to think of bathroom mirror, Taryn, when you look in the bathroom mirror and you see a reflection of yourself, where is your image relative to you? So if this is the surface of your mirror and you're standing here, where do you see your image relative to the surface? In the center of what? Right here? Right on the surface? I don't know. If that's where you see it, then okay. Mitch, go ahead. So you're standing here. Here's the mirror. And you see, oh, look, there's me in the mirror. You see your image. Where does your image look to be relative to the surface of the mirror, which is right here? And you're standing arm's length away from the mirror. Where does your image look to be relative to the surface of that mirror? So your reflection looks like it's arm's length away from the mirror. If I step away from the mirror, what does it look like my image does? So it looks like your image steps back away from the mirror surface more. So the distance the object is from the surface of the mirror, how does that compare with the distance the image looks to be away from the surface of the mirror? So if I am a meter away from the mirror on my side, it looks like my image is a meter away on the other side. So equal distances from the surface. Does that sound logical, Taryn? When you visualize it, can you kind of picture that and say, yeah, that sounds more like what I was thinking? So here's my object. I want to have the image and figure out how the image appears equidistant away. So let's make a copy of our image and we'll put it roughly equal distance away. We're not sure that's equal distance. Does that look like it's about the same height? How do I figure out where it goes? Well, this is one of the readings. It's in Moodle, and so if you want to go and look at this in a little bit slower speed, you're welcome to. Here's my mirror. Here's my object. Light rays are going to come out from the object in all directions. We're interested in the light rays that hit the edges of the mirror, because if light rays hit the edge of the mirror, then they can reflect back to create the image that we're interested in. So we're going to create light rays going from our object to the mirror. So we're going to create a light ray coming to that edge of the mirror, and we're going to create a light ray from our other end of our object to that end. We're going to put normals in. Why would I want to put normals in my diagram? Let will reflect, why would I want to have a normal in my diagram? What will that help me draw? So the angles will be as close to the same as I can do it freehand. Exactly. So here's my incident angle. I want to do a reflecting angle. So let's pick a different color. Does that look about right for reflecting? What my brain does is my brain backtracks the reflecting light rays to create the image. So I'm going to take this and I'm going to backtrack it. And I'm going to take this light ray and I'm going to backtrack it. So what that means is one of my angles isn't quite right. So I want it about there. It's a little closer. Are the purple arrows approximately equidistant from the surface of the mirror? Because we freehanded our incident angles and our reflected angles, we're not going to get perfect. If we measured it with protractors, we would probably do a better job. The backtracking of reflected light rays is what gives me the formation of my image. Questions on where to find the image and how to make sure that you can draw it. All right, when you look at your bathroom mirror, is the image that you see bigger than you, smaller than you, or essentially the same size as you? Same. All right, plane mirrors have no magnification. That means the image is the same size as the object. Abdi, when you did the lab activity yesterday, was your image upright or was your image inverted when you saw the images on the screen? It was inverted. When you look in a bathroom mirror, Nathan, is your image upright or inverted? Upright. So a plane mirror has no magnification. The image is upright. So the two types of images we're talking about, the type of image you saw when you did the pinhole camera lab where you had the image upside down and it was on your screen, and the image you see in a bathroom mirror are two different kinds of images. And the types of images, the two types of images we're going to talk about are real images, and that's what you saw in the lab. A real image is created by real light rays. Real images can be projected or caused to form on paper, on a screen, on a wall, on your hand. You created the image on the screen yesterday. You created a real image. You could have stuck your hand there and seen the same image. You could have stuck a piece of paper there. You would have seen the same image. Real images can be projected and can be visible on a screen, a sheet of paper, a wall. Real images are inverted. Virtual images are a different beast. That's the other kind. Virtual image is the type of image you see when you look in the bathroom mirror. It is created by your brain, backtracking reflected light rays. You can't project a virtual image. The only place a virtual image occurs is in your brain. Virtual images are upright. So one way you can tell what kind of image you're looking at is to see, is it upright or is it inverted? If it's an upright image, it's a virtual image. If it's an inverted image, it's a real image. When we're dealing with mirrors, when we're dealing with eventually lenses, we're going to be talking about distances. And the distances we're going to be talking about are the distances between the surface of our mirror or our lens and the object. So the object distance is from the surface of the mirror, in this case, or the surface of a lens when we get to lenses, to the object, and we're going to represent it as DO. It's easier to remember when we do it that way. The distance from that same mirror or lens to the image is the image distance. We're going to represent that as DI. So image distance and object distance are going to be things that we'll need to measure in some cases, and those are the symbols we're going to use to represent. Questions on plane mirrors? The plane mirror activity that I was thinking about doing today, what I would like to do is plan on doing that Monday. The mirror activity that is up there for homework that's in Moodle would probably be helpful for you to go ahead and do that before you do the lab. That might make drawing the line ray diagrams a little bit easier when you get to the lab on Monday.